Alright, so today we are going to talk about virtual memory, but before we start, today is May the 4th, and May the 4th be with you. To be honest, like a lot of people have different reasons why they become a computer scientist. A lot of you are because you love games. Some of you might be interested about AI machine learning. Recently, I heard a friend of mine who is interested about computer science because he wants to be a vlogger or something. So, and he figured out that there are a lot of technologies behind that. So for me, it's not related to Star Wars because I think it's too old-fashioned. It's the last generation, right? And so I actually like Star Trek, The Next Generation. But here's the thing, a lot of stuff you want to go back to trace the seminal stuff, and for this kind of series, sci-fi series in a universe setting, then Star Wars is definitely the classic one that you should check. Although all the technology from my perspective is kind of outdated, and it's more about the politics is more about some other things, but it's a classic, so you have to check it out. So a lot of stuff in research or any subject that you are studying is similar to that in a way that there are a lot of old stuff. Yeah, it's kind of old-fashioned. We are not using that anymore. Or you think, well, it's not related to my current life. However, those seminal stuff, they are actually inspiring a lot of new stuff. So, and a lot of things that we are in use, they have roots in there. So that's why we need to study it. And one of the good example in this class is we have von Neumann architecture. And because von Neumann architecture, memory is a big part of it. However, memory is way too slow. So we start to build memory hierarchies, which mitigate the gap, performance gap between different components in von Neumann computer. And in the last lecture, we have been talking about a lot of stuff, how to optimize the performance of a processor like an NVIDIA Tegra processor with a lot of tricks, software optimization, especially to figure out what we can do to optimize our performance. And there are four ones that we have been looking. For example, for loop optimization, we look at loop interchange to improve the locality of the cache and cache locality of your program, and turns out that helps to improve the cache miss rate. We also have loop fission, which help us to improve the cache miss rate when you have limited amount of weight associativity. However, if you have a rich weight associativity cache, for example, like Intel or AMD processor nowadays, then loop fission, this kind of coding style, would actually increase the amount of instruction count as well as memory accesses, which is probably not a better choice. So we have to go back and look at that and make them loop fission. So there is no absolutely right decision of loop fission and loop fusion. It's totally dependent on what kind of target architecture you are going to run your code, as well as what your code looks like. So turns out that, well, it's a case that it depends. There is no golden rule that you should use loop fission or loop fusion for your code. And one of the real case that we try to tell you that, well, software optimization is so important is the matrix multiplication. So originally we have the matrix multiplication like left top corner, and then we use the block tiling algorithm to reduce capacity and conflict misses. And later on, we transpose the code, and then we also can change the locality of matrix multiplication. So now we are not taking a row and a column, but we are multiplying two rows, making them two vector multiplications, and turns out that the performance is a lot better than we used to have. So that's the example of an optimization that we had before in the last lecture. And we also have, so here's a summary of the optimization that we have learned. So we have shown you that, like by changing the data layout, for example, in database from from row store to column store, we can better fulfill a select statement, for example, and that makes your performance significantly better. And another one is like blocking algorithm, which we used in matrix multiplication, which help us to reduce the capacity miss and conflict miss. And there are loop fission, which help to alleviate conflict misses if you have limited weight associativity. However, if you have enough weight associativity, you want to take the opposite direction called loop fusion, and it will help you to reduce the capacity miss. And also we have the loop interchange, which help us to improve the conflict and capacity miss. There are a lot of hardware optimization, and a lot of people were thinking about, simply use hardware, then my code, better hardware can help me getting performance on my code. The answer is yes or no, because the hardware can only do very limited things. So for example, one thing that might help to improve your miss rate is probably prefetching. However, I also show you that different processor, different code, the effect of prefetching is also different. And another thing that, hardware also adds stuff like write buffer, banking, multi-pipelining, critical word first and only restore. It's all about reducing miss penalty. None of them can help reduce the miss rate. So you are the only one who can make that change. And the last discussion is at this one, right? What will happen? What will happen? So, okay. So, looks like we need a demo to talk about this. But before the demo, I figured out that I missed one slide. Let me grab that one slide. Where's that? So, for this particular one, okay, where's that one slide? Shoot. Okay. All right, just let me copy that one. That should work. Oops. Okay. So the last time we end at this one, right? Like if we have a program that consumes a large amount of memory, which surpasses the capacity we have, then what's going on? So the answer is that okay, is it running? All right, let me do this in the real machine. Okay, so for this particular program, if you count it carefully, this is the same code that as I have. Okay, is it running? Okay, so right now it is running this memory allocation instance. So we can check the result later, but the answer is that for that particular pieces of a code, it will finish. It will finish. It will finish without any issue. But it is just slow. It is just slow. Why is that? Why is that? We will talk about that later. However, there is another pieces of a code that I would like to invite you to think about. So for this particular pieces of a code, if you check the code, it's a very simple pieces of code. So first of all, I create many different processes. How many of you know what a process is? Okay, if you don't know, I think we have a bigger problem. Okay, so for this particular piece of code, we will create multiple processes, and each process will run this pieces of code. We create a random number within a process, and I will print my process ID, and I will have my, I will print out the value of the variable A and the memory address of variable A within this process, and sleep for 10 seconds, and then come back again and print it again. So right now what I'm inviting you to think is that if I have multiple instances of this program, what would happen?
Professor's always low.
Try now. All right, let's wrap up in 15 seconds. Oh boy.
Five, four, three, two, one. Time is up. Okay, let's see. Okay, definitely this is a question that we need some discussion. So why don't you guys go ahead and discuss with your friend for another 90 seconds and let me know what you guys think. You guys are so quiet. Is it because it's raining outside? But there's no weather inside. So go ahead and discuss. Apparently, you don't know the answer. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so after discussion, okay, apparently I think there are some issues with you guys in CS202. Right? We don't have a consensus here. So, what's going on? What if we just run a demo? Okay, is it finishing? Okay, so let me run this demo. So this is the code we are going to run, and it's identical to the code that was given. And now I'm running 4 instances, and as you can see, it's running on the same cluster that you guys are running. Okay, so what do you find? What's the memory address of each one? The A in each process. So we have the process ID, right? So there are indeed 4 distinct processes, right? The value of A are different because it's a random, right? You will be surprised if it's the same. What about the memory address? They are all the same. Okay. So remember we have a sleep 10, right? So after 10 seconds. All right. So for process 7471, the value is 101 something 027. 101 something 027, still the same address. 473, okay, the third one that has been executed. 148 505, 148 505, still the same address. 472 711 4251, 711 4251. 7474 103 8844, 103 8844, address all the same. What do you guys think? Then what do you guys think in the question? Let me check. So B and C, huh? So it seems like a lot of you believe the 4. Some instances will print the same value of A. Why? Why do you think that way? I'm curious. Why?
Isn't it possible for 2 garbage values to be the same?
Why?
Probability?
Probability? But, okay, given you have 2 to the 64 number space, how high is the probability? If you have a random number generator that is written carefully.
Is it because the same process?
What?
It's the same process as the
But some instance, right? Then that's a different instance,
okay.
right? Okay, so here's the thing. But why? Why everyone has the same memory address, but you can still obtain a value of each one? Have you ever think about that? What? Fork, but what does fork do? Create a process, but how does that help to ensure different processes will still have its own value on the same memory address?
When we fork, we only create a new control block, but if we don't write anything, we're still pointing back to the same original memory.
But what's the original, the same memory? What's the same memory? But okay, can you explain the bizarre of? Okay, so the most mysterious thing here is that, right? You have everyone printing the same memory address here, right? It's the same. But why we don't overwrite the other?
Because when the child edits the value, it copies because it's writing.
Where are we copying to?
We copy over the memory
But it's the same address.
from the parent.
But if there's only one address, how come they don't overwrite each other? Have you ever thought about that?
Because it's, like I said, it's virtual, so
It's virtual, right? That's the thing I want. And that's the topic we are going to talk about today. The address you are seeing in your software is not the real address where your data is stored. Let me say that again. The address that the software programmer or the program itself sees is not the real memory address where your data is stored. Make sense? So what does that mean? So nowadays, when we create a process, or say a program A, right? When we start to run it, the system will create an instance of that program. That's called a process. And so if I have two different programs, obviously I have two different processes. However, when I create a process, in the operating system abstraction, I will create a virtual memory address space starting from 0 to the end of the available address, only available address. So for example, if you have a 64 address space, what will happen is that I will create an address space from 0 to 2 to the 64 minus 1, regardless how many physical memory is installed. So if I have two processes, I will create two of these spaces. So now I have 2 times 2 to the 64 addresses. However, each of them can only use their own zeros to 2 to the 64 minus 1. And then what will happen is that, for example, if now a programmer wants to load its code, and if you check the compiler carefully, I think one of the assignment would ask you to do that. So if you check the compiler carefully, you'll figure out that you always there is a default place for each program instruction starts. That's called a text section in the compiled program. And there is a contract between the compiler and the operating system where we should put the first instruction. So everyone's first instruction would actually start with the same address in a virtual address space. And when we want to load something into the system, we are considering loading it to the virtual memory address space. And your physical memory is only considered as a cache of your virtual memory. So what does that mean? If the memory page, which is similar to the concept of blocks when we talk about cache, in main memory or virtual memory abstraction, we use page as the very basic unit of access. So when I am accessing a page, if I couldn't find a page in a physical memory, that's called a page fault. And then my operating system together with my computer architecture, the hardware, will figure out how to fetch that page from your virtual memory abstraction, which typically you will put it in your disk, and load it from your disk or your persistent storage or somewhere you use as a virtual memory. Load it to the physical main memory whenever the page is referenced. So if I reference this page now, this page would go into the physical memory, and then gradually I will fill in this content into my physical memory. And if another program uses its own page, again, I load it to the physical main memory. And if I have a data access, it also loaded to physical memory on demand, page by page. So that's how it works. Very similar to the cache, right? So now you can imagine, here's the thing. Virtual memory is the universal set of your data and instruction. The physical memory, the DRAM that you installed in your computer, acts like a cache of your virtual memory content. And this idea is called virtual memory. And if I am running out of space, then there is something called swap. You can create on your disk that stores the stuff that you kick out from your memory. And whenever you need it again, we can put it back. So that's the whole idea about memory. And again, there are a lot of policies that you can use to manage your memory, which is now a cache of your virtual memory. So if you have been going through the operating system class, there are a lot of like algorithms, like clock algorithm, LRU algorithm, or whatever, right? So if you're interested, definitely take a look at the operating system textbook again. But this basic mechanism that I just described is called demand paging plus swapping. So that's the main idea how we manage virtual memory for now. So the high-level perspective is this. So although those programs, they may have the same memory address, like what we show in the demo, the address of A is 0x601090. Although everyone has this address, however, process A and process B, they both have their own virtual memory space. And with this abstraction, they will be mapped to different physical locations in your memory. So that's why if you write your own A, it won't affect other people's A. Because they all have although they have the same virtual address, however, they have different physical addresses. So that's why they don't overlap overwrite with each other. So virtual memory is an abstraction for memory address space that is available for programmers, software, your program. And every program in modern computers is queued using virtual memory addresses. The operating system and the hardware work together to handle the mapping between virtual addresses and the real physical memory addresses. In virtual memory, in this abstraction, we organize the memory locations into pages. So that's the basic idea. So as you can see, virtual memory has a lot of benefits. For example, if you have multiple programs, like what I just demoed, they can share the memory without any problem. The second thing, even though your application uses more memory than you physically installed, that doesn't matter, because as long as you have virtual memory abstraction, the hardware and the software will handle this dynamic mapping, swapping between your data. But when you swap out, right, thinking about that, you are not having your data in the cache, then it's going to be slower, right? So the program will finish, but just slower. That's the deal of virtual memory. And to be honest, without the idea of virtual memory, there won't be any possibility of software industry like we have nowadays. Because right now, a lot of people, have you ever cared about the amount of memory you use in your program? No, you just write it, right? So, like, okay, I shouldn't entertain my former employer, but an interesting thing, like how many of you feel that Chrome is really slow? Right, be honest, I'm okay with that, because I also feel Chrome is really slow. But if you talk to everyone in Google, right, they just tell you, okay, I mean, everyone should have a machine with more than 32 gigabytes of memory. And that's all the machine they use to test the performance of Chrome, and they think it's okay. Right, and every machine we own has more than that of memory, so we thought the rest of the world should act like that. But the answer is what? And that's not true, right? And we are, turns out that if I run this program with huge memory consumption to a smaller, a computer with smaller memory, then turns out that, well, the Chrome with this cube is just slow, right? But it will work. That's the magic of virtual memory, right? And the other thing is that it decouples the software development with the hardware architecture. So that's why you guys are less aware of what kind of underlying computer you are working on, because I just compiled the program and the program is portable, because we have a contract we support this memory address space, and everyone's program start with this particular address, and it will work on whatever computer. That's the magic of virtual memory. But without this virtual memory abstraction, there is nowhere we can have the software industry. So it's very, very critical. It's very, very critical. So here's the virtual memory abstraction. You see this graph similar. And it's indeed similar to the concept of cache, as I said. But the biggest distinction between virtual memory and caching is that in the caching, we partition the virtual memory space into small cache blocks, or say cache lines. And each line is like 64 bytes or something. But in virtual memory abstraction, we again partition the same virtual memory space with another unit called pages. And each page is potentially kilobytes. And the most commonly used page size nowadays are 4 KB. And there are a variety of reasons of 4 KB pages. But one of the main reasons I can tell you is that because it's easy to manufacture. So if you check the DRAM hardware, typically each DRAM row or each word line of the DRAM is 4K wide. And that's a performance optimization. That's a performance optimization that we figure out that that's the best balance of performance and cost. So 4K is like a general consensus between software and hardware. Okay, we use this as a good size of the page size, but there are a lot of different needs nowadays. So we can talk about that later, or in the paper that you read, they also mentioned. But here's the thing, for every data that you are accessing. So similar to the cache, right? Previously we said, even though I just want 1 byte of data within a block, I load the whole block. Similar here is that even though I just want 1 byte within the page, I'm going to load the whole page into the main memory, because the main memory can only store your data on page basis. And then to maintain the abstraction between virtual addresses and physical addresses, unlike cache has a separate tag array. In the main memory abstraction, there is nothing called tags. So we have to create a virtual data structure, which also resides in the virtual memory abstraction, surprisingly, called page table. So whenever I load a new thing into the physical main memory, the page table will record the specific location of your virtual address in the physical memory. So this idea is called demand paging, because we only load a page into your main memory when the data is on demand. And the block size, you can consider the block size is now the page size. And the page table acts like a tag array. So it's essentially a cache of virtual memory. And you might ask me about what's the way associativity, right? Because C equal to ABS. So the answer is that the physical memory actually implements a fully set associativity cache in a way that when you load a page, the page can go anywhere in your physical memory location. That's different from the cache, because cache is like a hash structure. So it can only go to the set where the hash index indicates, right? However, for demand paging, you can go anywhere. So that's the main difference. Now, okay, so how to translate the address? We say we have a page table. So let's start with a naive page table. So since we have virtual addresses that we need to map to physical addresses, so the basic idea is that, okay, I partition the virtual address into page number and page offset. And because page offset, right, again, similar to the idea in a cache, it's within a page. It's the location of your data within a page. So everyone within the page would have the same prefix. So that common prefix is called virtual page number. So we use the virtual page number as the index to look up the page table. So for example, now I have this 0B as the page number. which tells me that I should go to the 11th entry in this page table. So when I go to the 11th entry, I will store its physical page number inside this entry. So when I use this physical page number, I concatenate that with my page offset. That would give me the exact physical address that I need to access to find my data. So that's the concept, very, very basic concept of page table. So now, let me ask you this question. In a common system with 64-bit virtual address space, how big is a page table for a process? All right, looks like 35 of you already voted. So wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so this is what you guys think. Okay, most of you think the answer is B. But can some of you tell me why the answer is B? Why do you think it's B? Or you just guess? Can you tell me? A lot of you pick B, but why? Why B? Alright, I feel like Aaron didn't show up the last time. It's because I keep asking him in question. So Andy, you pointed to Ryan. Are you Ryan?
Shishin.
Oh, Shishin. Okay, where's Ryan? Okay, he disappeared because I asked him a lot of questions last time. Andy, what do you think?
Well, I think first the 4K bytes for each page
Mm-hmm.
is 4 times 2 to the 10.
4K. Say again.
It's 4 times 2 to the 10.
2 to the 10.
Did I do wrong?
Okay, so let's go back to the concept of page table. What's the purpose of page table? What's the purpose of page table? Why do you need a page table? What do you want to look for?
To translate the virtual address to the physical address.
Okay, if I want to translate the virtual address to physical address, how many entries do I need in a table? exactly the same as physical. But when I do translation, do I translate from physical to virtual? What is the address your software uses? The virtual address. So if every program says virtual address, what's the translation direction? Virtual to physical, right? So how many entries do you need?
64 bytes.
So it's a
64-bit memory addresses, right?
so you have a total of 2 to the
64 memory addresses, right? And each page is sized as 4K.
So it's
2 to the
12.
That's 4K. You need this many entries.
Times each one is 8 bytes. How big is it?
So the answer is that you need 2 to the 55 bytes. It's 32 petabytes. So none of you get that right. A lot of you guess it's gigabyte level because you think I only have this amount of memory. So it must not be larger than that. But what I'm telling you is that you guys are wrong. The page table needs to be this large if you don't have any optimizations. Your page table has to be really large. And plus, this is a page table for just one process. If you have 5 processes, 5 times 32 petabytes. Did you see the problem? We are not going to store the page table itself. So the virtual memory abstraction cannot be maintained if the page table is not there. So that's not going to work, right? And if you still don't know why, 202, take it. Okay, so conventional page table has two main problems. First of all, it's a very genuine table and it's consecutive. So what does that mean is that you have to preserve a consecutive area in your main memory to store the whole table, which is almost impossible because I don't even know how many programs that I want to execute. However, that's indeed what early architecture does. So, early operating system does. So if you look at, how many of you read the THE paper in operating system class? Okay. So Dijkstra, how many of you know him? Yeah, he is actually the seminal researcher in operating system. He wrote a paper called THE, and that described the very first operating system they developed in their lab. And that actually also, that's a very elegant paper. You should definitely check it out. Not only the operating system, but also the mutual exclusion algorithm comes from there, as well as the idea of layering in software engineering. So that paper itself covers a lot of things that actually torture us a lot in learning operating system software engineering and algorithms. So that's definitely a very seminal paper that was done in 1960. However, in the THE paper, if you check the paper carefully, they can only support up to 5 processes because they have to always make sure that each program can only use this amount of memory in this area. So they have to, because they don't have the demand paging idea yet. Okay, but for conventional page table, you need a big segment. They have to be consecutive, so difficult to find a spot. Second, the whole thing is just too big, 32 petabyte. How are you going to fit in your installed memory? So that's not going to work. So here's the solution, right? Let's think about doing it in a different way. So first of all, if you want to break up a consecutive, saying that, okay, if I cannot fit everything in a consecutive array, what will you be doing? What? Hash is still an array, right? What's the data structure you will be using? Tree, right? So, first of all, if you want to build a tree, you have to count how many leaf nodes you need. So again, because we need to address this amount of entries, right? So this is the total number of entries that we need to use to have. So these are the leaf nodes that we need in a tree, right? We need a total of 2 to the 64 divided by 2 to the 12. However, that's very large, right? So first question is that, do we really need to use a very large table? And the answer is probably not. So this is your virtual memory space. However, if you have some idea about the compiler and the operating system, what will happen is that, first of all, in the very beginning, I'm going to load my code and my global variables, which are static data, into the virtual memory address space. And the standard addressing, the contract is that we always put your code and data starting from the very beginning of your virtual address space. So for each compiled program, the first section is the text section and then the data section. However, most of the time we are going to have local variables. We are going to allocate memory data structures dynamically. So we have two types of data section going after the static data. So one is the heap, the other is the stack. So for the heap, it's used for allocating memory addresses for globally visible data structures. So for example, if you do malloc or calloc, your data coming from the heap space. So that's why in your operating system you have to maintain 2 pointers for each program. One is the heap, the beginning of the heap and the end of the heap. However, if you have a local variable, it goes with the stack. That goes from the bottom, or say the very top of your virtual address, depending on which side you want to see it. I like to put it in a very at the very end, but if you look at the address space, it's actually at the very top. So what happens is that when you gradually allocate data, that goes from the beginning as well. And then if you are allocating local variable, it goes to the very end. So what does that mean? There is a joint middle section you never use. You never use. So if I can find a data structure or a way to avoid this joint section, I can just create entries sufficient to accommodate all the virtual addresses that I need, instead of every virtual address in the page in the virtual address space, right? And if you still cannot understand what's going on here, operating system class, okay? So right? And even though you think you are creating a program with 1 terabyte, but considering the 1 terabyte, it's only 0.00006% in the address space. So you can think it's a huge saving of page table size if I can only capture the part that I need for the virtual address. And the other thing is that we cannot find a big segment for storing consecutive data. So it turns out, again, if your memory structure is paged, your hardware structure is paged, we also need to break up your page table into pages. So what will happen is that previously we mentioned you have this many entries that you need to store. However, well, if we want to use page as a unit of storing page table translation entries, how many can we store consecutively in each page? So the answer is that because your page size is 2 to the 12, and if you're addressing a 2 to the 64-bit address, you need 8 bytes to store an entry. So it turns out that you can store 2 to the 9, 512 page table entries in each page table node. So each leaf node in your page table now is storing 512 entries. And so what happens is that if I have a code section, right, then I allocate a page table entries that contain the translation of the code section on demand. And if I have a data section, similarly, I just gradually build up this table entries for these areas that I need. And for those middle sections, there won't be any node created. So that's the idea of how we save space. Now, we have a lot of scattered page nodes, right? We have a lot of scattered page nodes, right? How can we locate them in the main memory? So here's the thing, why we need tree structure. And if you think about the nature of the node that we have, each page contains 512 entries that point to other places. So that's exactly a B tree structure. So our idea is that we just leverage this B tree structure to build a hierarchical page table. So the idea of B tree structure is that, okay, right now, in the worst case scenarios, you have 2 to the 64 divided by 2 to the 12 page table entries that you need. And we have a total of, so it turns out that for each node, you are storing 2 to the 9 entries. So if it's a B tree, it needs this many levels in total to address everything. So what happens is that for a hierarchical page table, you will create a B tree with this many levels to index your virtual addresses and find a translation at the end. Okay, so you read this paper, right? What happened in x86 right now? Okay, first of all, although it has a name of 64, it only supports 48 bits of memory address space. For a silly reason, because they don't believe anyone would need more than 2 to the 48 for now. So let's live with it. So for x86 processor, what will happen is that when a processor is designated for a process, the operating system will program its CR3 register. And this CR3 register is nothing but a memory address pointing to the root node of the hierarchical page table trees root node. So this is a memory address pointing to a root node, which is again a 512 entries page table node that would point to the next label. But how do I know where in the next label should I visit? You use this part of the index. And again, because you have, for 48, right, you need 9 bits in each label of index. So you use these 9 bits, and also because you have 2 to the 9 entries in each node, so you have 9 bits in index. So you use this 9-bit index to figure out where in my 512 entries would contain the pointer to the next label. And then you go to the next label. It's another node with another 512 entries. And then, again, use the L3 index to find out where in the 512 entries can I find the L2 table. And the L2 table also use L2 index, which points to the next label. And the next label, because it's the L1, is finally where I can find my translation. Right? Then I can find a physical memory page number concatenated with my offset. So that's how London x86 processor would translate your address, by traversing this hierarchical page table. So now I have a question for you. For a move instruction, how many memory accesses in total do we need? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, looking at your answers. Okay, so I think it's better to have some discussions. So why don't you go ahead and talk to your friends within another 90 seconds and see what you guys think after this discussion. Go! Make sure I hear your voice. Louder, louder, getting louder. Where's your voice? Alright, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, after discussion. Do you guys really discuss? Slight change, huh? So more of you think it's C. What is C? C is 6. Can I have some of you telling me why do you think it's 6? Why do you think it's 6? Why do we need 6? Come on, you discussed, right? What's your name again?
Ivan?
Ivan. Okay, sorry.
No worries.
Okay, what do you think?
Well,
Because-
originally I said 8 because we would need to go
Mm-hmm.
access page table, so the 4 levels
Mm-hmm.
to get the information, and then
Mm-hmm. 4 levels.
again another 4 levels to place it, to know where to place it. But then when talking
Mm-hmm.
my friends here, they said that it would make more sense for it to be 6, since we would need the 4 from the page table,
Mm-hmm.
and then 1 from the index,
1 from the index.
and then I believe it was 1 from the actual access.
Okay.
And So they convinced me to that one because that made more sense.
Okay, so
What happened?
right? So this is the translation. So this is 1, this is 2, this is 3, this is 4, and when I get this address, there is another physical memory address. That's a total of 5. Okay. Who lives in virtual address? Go back and look at this graph. You have code, you have data. What's a move instruction? Where is the move instruction? It's also in virtual address, right? So the right answer is that we have a total of 10. Okay, how slow is a memory access? A memory access is, okay, from your homework too, right? We have highly optimized memory subsystem. Memory access is 14 nanoseconds. If you have 10, it's 140. So, with virtual memory abstraction, each memory access will take 140 nanoseconds. That's 1,000 times slower than your processor speed, or 2,000 times slower than the processor speed. If you have a faster one, come on, this is not going to work in terms of performance. So, we need to figure out if there is any way we can avoid the address translation overhead. So in Dr. Lamson's the philosophy of system design, he said that one of the good ideas that you should use again and again is caching. So if translation is slow, let's make a cache for it. So this cache is called translation local site buffer. So this is a dedicated cache for storing the virtual to physical address mapping with a few entries in SRAM again. So your cache now is more complicated in a way that, okay, not only L1, L2, I should have a TLB. So that, since your program is executing in virtual address space, whenever I execute an instruction, I have the TLB give me the address translation and fit it into L1. I so envy your face, you don't like it, I know, because I don't like it either. Because the best thing is that right now, this is already slow. Right now, we are adding one more thing in there. It's going to be slower. So that's not what we like. Okay. So, another idea is that since you have virtual addresses used by your programs, and the issue is that we need a physical address. So the idea is that, okay, what if we just let the L1 cache use the virtual addresses as well? So what would happen is, okay, I just fit virtual addresses to both L1 and TLB. And only if the L1 is a miss, I would use the physical location as the memory request to L2. Is this a good idea? So this idea will work if you only have one process. But if you have multiple processes, right? Everyone has the same address of variable A, don't you remember that? How can I tell who is in the cache if you just have virtual address? So that's not going to work, right? So what you really need to use is physical addresses. You really need a physical address to make sure that that's exactly the data you are accessing. So here comes the idea of virtually indexed, physically tagged cache. So the idea of virtual index, physically tagged cache is this. So first of all, if you're carefully observing your virtual address and physical memory address, which part remains the same in physical address after translation? which part in your virtual address and physical addresses are the same? Page offset. Awesome, right? So page offset is the same. Physical address is the physical page number is the only one that is changed, or virtual page number. That's the change, right? So here's the idea, right? We want to avoid the address translation when we access L1 cache. And remember how we access L1 cache. When you access cache, what are the stuff you do? You got an address, you partition the address for what? You partition the address for what? The index. What do you use the index for? Which set, right? Awesome, you are ready for midterm, I believe. Okay, so you partition the address simply because first I want to find out which set may contain my data. Okay, so that's the key thing, right? If I want to make sure that I would access the same set as I access no matter, like, okay, so if I want to make sure that I will always access the same set, no matter I use virtual address or physical address, then I should find a way that I can ensure the set index resides in this persistent part during address translation. Agree? So, here's the thing. What if we make block offset and set index? They are both parts of the remaining parts, unchanging parts. So, you can first use the set index and the offset to address which set may contain my data, where in the block I have the data. And then, during this period of time, I perform the table lookup, or say the TLB lookup, and compare the tag later on. So that's the idea of virtually indexed physically tagged cache, is to use the unchanging part in your virtual address as the index and a block offset to access your cache, and then your tag still store the physical tag so that I can avoid or alleviate, reduce the translation overhead. So what happened here is this graph. So again, with a virtual address, I partition the address into set index, block offset, and virtual page number, and assume the set index and block offset, they all within the page offset. And so that I can use the block offset and the set index to find out which set of data I have. In the meantime, I'm using the virtual page number to figure out the physical page number of the page, and then compare the tag, which is essentially now the physical page number of your block. And then I can tell if it's a hit or miss. And in the meantime, it allows the TLB lookup to perform in parallel with the L1 access. Okay. But here is the restriction, right? So say that if I have a 4 kilobytes of page table, it tells me that the log S plug log B, they must be fit in to 12 bits. It must fit in 12 bits, right? So if today I want to build a cache, and according to C equal to ABS, what I can do is that I have to make a cache C equal to 8 times 2 to the 12. So if I have a direct map cache, I can only make it 4 kilobytes. So now I have a question for you. I want to build a 30 kilobyte cache with 4K pages. What what is the available choice that I can do? Alright, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, let's see. So looks like we missed some discussion. So why don't you guys go ahead and discuss with your friend for another 90 seconds and we will see what's going on. Alright, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, what do you guys think? After discussion, more of you think it's C. But how? How to solve this problem? First of all, right, here's the thing. It's 4K pages. So we know, first of all, log B plus log S must be 12. That's the restriction. So how about the first one? If I have 32 kilobyte blocks, two-way cache, C equal to ABS, will that give you that? So C equal to ABS, right? It's a 32 kilobyte cache. So 2 to the 5 times 2 to the 10 equal to, okay, let's say now it's 2 times A 32 byte. So it's 2 to the 5. So this get cancelled. And so the S would be 9, right? So 9 plus, if it's 32 kilobyte, 5, what is that? That's 14. So A is not the answer. Okay, the most popular answer is C, right? C equal to ABS. So 2 to the 5 times 2 to the 10 equal to, it's 4-way, so 2 to the 2 times your block size, 2 to the 6. So your S is what? 2 to the, so 15 minus 8, that was 7. So 7 times 6, what does that give you? 13. So C is also not the answer. Another lesson learned, if you see multiple choice questions in the midterm, don't pick C. I hate C, by the way. Right? So that's not the right, so I don't, so, right, do discuss, right? So the answer is D. Right? If you do the math, right, C equal to ABS, you will find out. Okay, let me show this. You will find out, right? C equal to ABS, and if A equal to 8, okay, if you have, yeah, so 2 to the 12, right? And it means that if you want to build a 32 kilobyte cache, you can only have 8-way associativity. And that's exactly how Core i7, or if you check the cache configuration of the AMD Ryzen machine that was given to you, that's exactly how their cache are designed. So a lot of you might say, why don't we make bigger L1 cache? Because we can't. Just because we can. Because there is such a guy called virtual index physically cache. Type cache is limiting the cache size. So L1 can never go bigger unless you increase the way associativity. However, increasing the way associativity is very expensive. So we're not going to do that. So that's why we need to make a code that require just enough way associativity we provide to make sure that your capacity fits in L1, and to know how good you are at that. We need a midterm to make sure that you know that. So here's the midterm. We have a total of 16 multiple choice questions. It's pretty much like the in-class question or the reading quiz question. We have 3 short answer questions, and don't take a photo because it will be online, okay? And the homework, I will give you the higher resolution one, so don't need to take the photo. I will have homework style correctness question times 3. And again, a lot of you are saying that, oh, I didn't put this in my assignment, sorry. Typically, if you have that regrading request, I would turn down because I will do the same in the midterm. So the standard that we are giving you in the assignment, that's actually the standard requirement that I would like to see in the midterm. So that's why we have this grading criteria that we made, and we want to ensure that you guys provide that in the assignment, because the assignment is to practice you for the midterm. So any regrading request like that, I will reject. And I think our TA did a great job in that. Okay. So again, you have to show what equation you are citing. You have to show this is how you substitute the numbers with this equation terms. That's how I like to see. Sample midterm. So first of all, we will have 16 questions, multiple choice questions. So again, they are just sample questions. So, and they are from your slides. So don't ask me for answers because you should be able to find them in the previous slides. Sample short answer questions, I will pick 3 out of this list. What is end-loss law? What is performance equation? As you should know, 2 things affect each term in the performance equation. Difference between latency and throughput, whatever. What is benchmark? What is important? Why T-floss or IPS sucks? Alright? End-loss law, right? You see this in your homework. A lot of you struggle with it. I will definitely pick the one you struggle the most. Right? So make sure that you know why the answer looks like that in your assignment. Speed of y over x. Right? I like that. How can we, well, the other CPI, right, cache simulation, right, those are the topics that I like. All right, so here's the thing. We will have assignment to do tonight. Start early. Well, if you haven't started, starting it now, right? And if your question cannot be addressed online, we have office hours. That's why they are there. And midterm next Tuesday. You can only take the exam in person. It's closed book, closed note. We will check your student ID. If you don't have your student ID with you, we won't let you take the exam. We won't let you take the exam.
Is the exam on paper or?
It's going to be on paper. And it's going to be on paper. Yes, question. What? The solution will be released on Friday.
Oh, like tomorrow?
Yeah.
Okay, and then do we need a scantron?
What?
Do we need a scantron?
You don't need a scantron, but make sure that you put your answer in the box that we draw.
Does driver license work? Same name?
Okay, driver, where's your student ID?
I lost it.
You lost it. Okay, driver license. That sounds okay. What else? Okay, if no question, enjoy the rest of your week and good luck on your final midterm.